Hi, everyone. So I have lots to say, but at least today I want to give you an idea of what is the F monad, what is that thing, and how the F monad can be compared to monad transformers, and how it might actually be a better solution than monad transformers. So I'm Eric. I recently moved from Sydney, Australia to Berlin to work for Zalando, which is a fashion company, but it's also actually a very nice tech company. So I encourage you to come to the booth and discuss with us after the talk. But more about other things. Anyone has an idea who wrote this? It's all about effects interacting together. And the person who wrote this is actually the first programmer ever in history, Ada Lovelace. So she was trying to implement some algorithms based on a machine that was not even really existing. And she was having all sorts of difficulties with side effects and variables influencing each other. And I mean, I had the same issues. I come from a Java background, and I've dealt with side effects and effects of all sorts. And after a while, I got really fed up with it, and as you must have, as many of you must have. So I decided after a while to go from something saner, something bringing me calm, serenity. That's functional programming. And functional programming is like the best idea in the world. Just have functions, you take inputs, and the output only depends on the input. It's on the paper, it's simple, it's nice, and it looks great. But actually, if I leave you in a room with a computer and just functions, after a while you realize it becomes tedious. You realize that you need to pass state around. And you start wondering, how do I even do things like I/O? I mean, I still need side effects of some sort after a while. So probably after a while, you would come to invent monads on your own. And you would call that a monad if you have the genius of this guy. That's Philip Wadler. So Philip Wadler, more than 20 years ago in this paper, presented the idea of using monads for functional programming. And he started with a very simple example. And probably his paper is better than any kind of blog post you could read on the subjects presenting monad as burritos or whatever. Just read this paper, it's actually pretty good. And he starts with an expression representing divisions. So you have an ADT, a data type for this, representing those divisions, and a function to evaluate them to a double. And that's all good, it's all pure, it's all nice. But of course, with divisions, you cannot divide by 0. So what do you do in that case? And you cannot throw exceptions, because again, it's pure, no side effects. So what do? Well, you represent exceptions. You say, what does it mean to be an exception? So you have basically two cases. Either you raise an exception and you have a message, or you just return the value. The value is OK, and you can proceed with that value with further computations. And so let's start to use that. And it becomes ugly at this stage, because you need to start to evaluate the first operand A. You might have an exception there. So, OK, in that case, you stop, you keep the exception, and then you evaluate B. You might also have an exception. And then you come to what you really want to do, which is the division, and check if B is equal to 0 or not, which is kind of the important part. The rest looks like boilerplate, right? Same thing if you do states. So if you want to count the number of divisions in an expression, you can use, so this is how you encode states using a functional pattern if you want. And you can do the same, but again, you have all sorts of boilerplate. So the trick and the nice thing about this paper and the idea behind monad is that you can encapsulate all those things behind two generic operations, one called unit, the other one called flatMap. And then you rewrite your evaluator to return something that's an exception of double. And you can use for comprehensions. And I mean, I guess many of you know all about that. But the important thing here is that what we return is an exception of double. So what have we done here? Instead of just computing with values, we are now describing more general computations. We are describing values with effect. And we are using a type constructor, that's exception, to denote what is the effect here, right? So it's all nice. Now we have a way not only to express values in pure functions, but we also have a way to describe effects. And so you read the paper and you think, but OK, what's the next step? Can I have exceptions and state at the same time? And you don't have the answer in the paper. So is it possible to really have both in the same computation when you want to compose those two things? That would be nice, right? So the first idea that can come to your mind is, OK, maybe we can stack them. I can have one inside the other, a state of an exception or something like that. So people started working on that, and it's actually 20 years ago they started working on that, and describing what are monad transformers. And one obvious question arises right away is, okay, in which order should I put those things? Which order does make sense or not? Should I put the exception inside the state or the state inside an exception, right? So let's play around with this and see what we can do. So actually, this one doesn't work. You cannot put a state inside an exception because it's just not possible to write a flatMap method for this. And I really encourage you to come back home, try to write a flatMap method and see why it doesn't work, because that doesn't work. Because eventually you end up with an expression like that, which you cannot really flatten. It doesn't work. That's unfortunate. Fortunately, this works. So you can encapsulate a function that's going to take an int and return an exception of a state. That one works. But we are still left with two possibilities, with two possible ways of stacking those two things together. So which one is the best? Or are they different? I don't know. Let's try. Let's see what happens. So let's take the first one where we can say that inside a state, we can have some exceptions. So we create two methods. One called put, to set a new state, and another one to raise an exception in a computation. And let's use them. So let's say I put 10, then I raise an exception, and then I put 20, and then I'm done. If I run this computation, I'm going to end up with an exception, and the last state I've set just right before I raise the exception. That's what I have. What happens if I do the other way around now? I put an exception around the state. And so I need to re-implement put, re-implement raise, and I write the exact same expression where I put 10, I raise an exception, I put 20, I'm done. And now the end result is just the exception. I've lost all state. So we have two very, very different semantics here. One you could call imperative semantic, where when you raise an exception, you get the last state that was known at the time. The other one is more like a transactional semantic, where when you raise an exception, you lose everything. You roll back. So the order in which you evaluate your effects is really important. Whatever you do with monad transformers, with the F monad, the order is going to have an impact on the final result. But there is a good thing about the data structures I've described before, exception state and state of exception, is that they can be generalized. So exception state can actually be generalized to exception T, taking any M that's going to be a monad and transforming it. So this is where the name monad transformers come from. At first, I was a bit scared by this term. I couldn't understand what it means, but it just means this. You have a monad, and you transform it, you add an additional effect on top of that monad. And because this is a transformer, you have the end result will still be a monad. So I can put any M I want, as long as it's a monad, exception T of M will still be a monad. It will be the same monad plus an additional effect, that is, I can raise exceptions. Same thing for state T, I can have any monad. If I add state T on top of it, I can handle state, I can store state, I can get state, and so on. So that's pretty cool. And then I can describe stacks like that. I can stack those things with as many monads as I want. But we see right away that there are some costs associating to all of this. So one of them is that we are building those values that are deeply nested with each other. So I have the exception is inside a state, and if I put a writer on top of it and a reader on top of that, those are two other monads, I will have values that are really deeply nested. Every time I do a flat map on those things, that means that I have to go inside each of those values, call the flat map for the corresponding monad, and flat map again, get the result, and then flatten back the resulting structure. So you can think right away that there's going to be some kind of runtime costs when you use monad transformers with big stacks. That's an important thing. The other thing is that, especially in Scala, there's a developer cost, because you see that I'm using those question marks in the types here, and those question marks are brought to me by a compiler plugin that's called Kind Projector. That's very useful for partially applying types like writer, reader, and so on. The only thing is that even the compiler gets lost when I have big stacks like that. So I have to break out my big stack into smaller things so that it compiles. Otherwise, it doesn't compile. So that's so that means that monad transformers, they have a cost in terms of cognitive load for your development. There's another cost, is that when you have stack of effects like that, and you want to take a single effect, like state, exception, reader, writer, you need to lift it. So you need to create a value of that bigger stack and know exactly at which level you want to lift it. So you need to define all sorts of crazy lift operations, and maybe you need to lift and lift and lift until the value goes at the right place, and then the compiler is happy. And it feels like, again, boilerplate, not very fun thing to do. And then you have other questions, like how do you handle effects which look kind of similar? Like you want to have two readers, a reader of an int, a reader of a string. How do you put them in the same stack? At which level? Is the type inference going to be happy with that or not? It's not completely obvious. So in practice, what happens in practice is that the best way to deal with this in Scala land is to build your own stacks for whatever you have to deal with all the effects you need. So let's say I need to interact with Hadoop. I'm going to create a Hadoop stack that's going to contain all the things that I need. I need a reader effect to get the Hadoop config. I create a function giving me this Hadoop config. I need some error. I know that I'm going to do some I/O. So I build my own custom stack to interact with Hadoop. If I need to interact with S3, I can do the same, but this time I might use futures instead of I/O as my kind of base execution monad. And on top of those stacks, you will add all sorts of specialized functions to nicely encapsulate all those functionalities. So functions to get the config back for Hadoop, functions to raise exceptions, functions to take an I/O value and put it in the stack, functions to take something which is possibly an error, put it in the stack, and so on. And maybe you can add some map values to map different things, like transform the error into a different kind of error, things like that. So that's all going to be helpful, and it actually works. I mean, you will have no problems with type inference. You can define lots of small and useful combinators where you can essentially have all those effects working well together. But you start having problems when you want to mix those things. They are not really composable. So if I have a Hadoop stack on one hand, if I have an S3 stack, and now I want to take some files from S3 and I want to push them to Hadoop, how do I do? Well, I'm back to square one. I have to redefine a full stack again that's going to have all those effects together. And I need to decide, okay, do I want those things to happen in I/O, in future? And then I need to write some helper functions to inject now a Hadoop thing into Hadoop S3 stack, S3 thing into Hadoop S3 stack. And I need to add all sorts of boilerplate code now to be able to lift all those things into a wider stack. That's not fun. So is there a better solution? Is there something else than monad transformers? Is there another way to see the problem? And it's actually pretty interesting that in the first paper on monad transformers, there was this note at the bottom on the first page saying, oh, those other guys, they are working on a different system. It looks complex. We don't completely understand how it relates to monad transformers, but that looks interesting. What is it? And it's really cool because now we're 20 years later, so we get the end of the movie. We know the end of the story, right? We don't have to wait for 20 years. We are 20 years later in the future. So now we know. And the result is the F monad. So the F monad is kind of the composition of different results, paper, result from research, resulting in one pretty nice way to handle effects, either in Scala or in Haskell or in languages like PureScript. It's almost always the same approach, implemented a bit differently. And to be able to describe what the F monad is, you need to describe those pieces together. So I'm going to try to give you at least an intuition for what this is. So we are still going to represent effects using type constructors. So if I have sum of 10, it's an effect, returning an int. And what is the effect of option? The effect of option is that computation might stop. If I have none, there's nothing else to do. I cannot go on with none. I need to stop there. And if I have states, something where I can store states as an int, that's also going to be an effect, and the type of the effect is state int in that case. So in the fmonad, we describe effects. But we do a bit more than that. We describe at the type level what it means to be a union of effects. So we generally, instead of having just one value and one possible effect as a type constructor, we describe at the type level that a given value can have a union of effects. It can have no effect, it can have one, or it can have several in this union. So it could have option only, state only, or both state and option. And that's what we describe at the type level. At the value level, we need to be able to put those individual effects into a bigger union thing. And we'll see exactly how it's done later. And then the idea of the fmonad is this one. Let's say I have a union of effects. In that case, it's simple. I just have sum of 10. And let's say I have a way to extract this 10, which is my value with no effects, 10. And I have a way to extract it from sum. And I have continuation to say what to do next if I have this value. What can I do next if I have this value? I can take this value and I can create a new effect, this time using state. And this one is just going to put the value I had before, store it, and return unit. What can I do with this unit? If I'm able to extract this unit, access it, I can take it and provide another option value, option effect with it. And if I'm finally able to extract hello, I will just return it. So basically, an F construct is one effect, as described as a union of possible effects, and a bunch of continuations that are going to tell you what to do if you can effectively run the effect, extract a value, and what to do next with this value. Let's see how this works. So I have sum, that's an effect, and the thing that's going to extract the value is an interpreter. So for each kind of effect, you will have a corresponding interpreter that's going to tell you what to do with this value. So in the case of sum, the interpreter is just, okay, I know if it's sum, just return the value. If it's none, you don't do anything. But if it's sum, you take the value and you apply the continuation. So we apply the next continuation, and then I didn't write the state interpreter is now going to interpret this thing as grab the n, store it somewhere, and return unit, and run the next continuation. Next continuation is again an option. We run the option interpreter, extract the hello, and this time there's nothing to do, just return it, and there will be a last pass of state interpreter to return the final state. Again, that's a bit fuzzy, but there's this idea that you have effects producing values, interpreters interpreting this effect. If it can extract a value, it's passing it to the continuation. Continuations produce additional effects that can be interpreted with different interpreters, and so on and so forth. So let's see if we can make this a bit clearer, maybe a bit more formal. So let's have another look at what is the option effect. And let's model the option effect like this. We say an option effect is either there's no effect, we just return a value, it's pure, nothing, or it's stop. We want to say now there's no more computation, you stop there. Or there's more to do, so a value will be available, and I store in the more constructor a continuation for saying what to do next. And I can implement those helper functions. If I want to implement the monad instance for this thing, what does it look like? Well, pure is just return. And if I want to flat map, if I have return, I apply F. If I have stop, I don't do anything. I just stay at stop, right? Meaning no more computations. And if I have more, I keep my value, but I just flat map on the continuation with the F. And this operation is actually interesting because it can also be written like that, with this strange, fishy operator, which is the Kleisli composition. And class-like composition is no more than regular function composition, going from A to B, from B to C, and then I can go from A to C. That's normal function composition, but this time with monads. So if I have a function going from A to M of B, if I have a function going from B to M of C, and if M is a monad, I know I can create a function that goes from A to M of C. I can do that. And the operator I'm using in that case to do this is the class operator. So how do I run this opt value? To run it, to evaluate it, to interpret it. If I have return, I just say, OK, now I have a value, so I create an option with sum. If I have stop, I return none. There's nothing else to be done. And if I have more, I apply the continuation to my value, and I run, again, recursively the interpreter, because I might have other effects, other optional effects to run. So now let's take this construct and try to make it more general. Extract a bit of the boilerplate that's in there in this sense. We just keep two values to describe the optional effect. We just say an optional effect is either you stop there, there's nothing else to do, or you have a value and you are free to do something with it. That's all there is to be done to describe what it means to be an optional effect. And we put the rest in a construct that's called f. So f is either a pure value or an impure value having some effects and some continuations. And a continuation is something like this. You can give it an x, it returns you other effects, and you can add a function a bit like flatMap, and it extends the continuation, gives you another continuation, this time going from A to B. And if we implement the monad instance for the f monad, basically it's pretty simple because pure is pure. When I want to flatMap pure of A, you just apply f. And if you have the impure case, you just add the function you want to use for flatMap at the end of the continuation. That's basically it. I mean, it's harder to make the implementation of a monad simpler than this, right? It's like the essence of what it means to be a monad. And now if I want to run my effect, and if I have this, pure case, I return sum. Impure with stop, there's nothing to do, I stop there. Impure with more, I apply the continuation, and I call the interpreter recursively. So what all that means is that with the f monad, basically you will never have to re-implement flatMap again. It's done forever. flatMap, the monadic clause, all of that can be verified once and for all. The only thing you have to focus about is the description of your effects. What does it mean to be optional? What does it mean to be an error? What does it mean to be a future? And for each of those effects, you might have additional laws that you might want to check. For example, for states, you might want to check that if you put a value A, and then if you put a value B, and then if you get the current state, you should get B. Right? That's one of the laws that you want to check. You want to make sure that this law will hold. The rest is boilerplate. It's done by the f monad. So the rest of all of this hangs with different constructs. One of them is a type-level description of effects. So it's a bit like using a h-list of values, but this time it's using a h-list of type constructors. Because, as I said, we're using type constructors to denote effects. So in the f monad, there's a way to describe like this, a stack of effects, all using type constructors. So at the type level, we have a way to track those effects. Then there's a way to relate values. So the union thing is how to put values inside a larger union of effects. And it's actually the more deeply you're nested into this value, the more, there's a correspondence between the nesting and the effect you're implementing. And then we need a member type class to say if a given effect belongs to a given stack. So we need to be able to inject an effect into a larger stack of effects, and we need to be able to take a large stack of effects and check if a given effect is present or not in this stack. And this is done through a type class. Then we can define functions like that. this one is send any effect into a larger stack as long as it's a member of the stack. And then we can re-implement all sorts of functions like ask for the reader effect or KO for the error effect. And now we can re-implement Philip Watzler example using both the error monad, both the error effect, and both the state effect very easily. Because we have different operators, like one to raise an error, one to modify the current state. And what we get eventually is this big thing having both effects. R has both effects because there are implicit values saying that. So if we try this on a few examples, maybe I should go back to the example. So you have 5, which is 10 divided by 2. You have 2, which is 10 divided by 10 divided by 2. And you have an impossible division because we have division by 0. If you try that with this stack, and you run the different interpreters, one for the disjunction, which is the error effect with XOR, one for the state, you get the value you expect, and 1 here is the number of divisions. For 2, you get the value 2, and then you had 2 divisions. And for the division by 0, you get an exception, and you just had 1 division up to that exception. Of course, the order is still important, so the order you run your interpreters as is important. So if you change the order of the interpretation, you will get different results. And in particular here, you will just get the exception. You will not get any more the number of divisions you had. So this is all implemented in libraries, and actually, because it's fun, and I love duplicating code in 2 libraries, one for cats and one for Scala Z. So you can have a look at that. And in those libraries, out of the box, there are a bunch of effects already there. So for state, for reader, writer, optional. There's an error effect which is useful for things like Java, where you can have exceptions. And so it's dealing with a distinction between exceptions and failures. There's a list effect. There's a non-deterministic effect, which is not shown here. So you can play around with this. And useful things that you can do with that, for example, is you can transform effects and inject smaller stacks into larger stacks. So if you remember the example with Hadoop, when we had effects for S3, effects for Hadoop, now if I want to compose 2 functions working in those 2 different domains together, I just have to describe, so those are the 2 functions I want to compose. So one is working on Hadoop, the other one is working on S3. If I want to compose them together, I can describe a larger stack with all the effects that I want to have, and I can put my previous functions as before, but I will just say, okay, I'll inject that into a larger stack. And it's going to do all the implicit and type-level machinery that's necessary for this to compile. And then you can run your interpreters to effectively run those actions by running each of these interpreters here, passing the actual S3 configuration, passing the actual Hadoop configuration, getting the logs, and so on and so forth. So, is it the best thing ever? Is it a silver bullet, the thing that's going to end all of our issues? Unfortunately, no, or maybe not yet. There are still things to be done. Implicits are a bit tricky, and actually maybe not, because thanks to Miles Sabins, so yesterday, or I mean a few days ago, he published a fix for an infamous Scala issue, which was SI 2712, which is kind of famous about type inference with type constructors with several type parameters. And that's an awesome fix, because this allows me to remove a bunch of horrible implicit definitions that I had before. So I think this is going to get better. We need to use it in production. I mean, it's nice to have a library. It's nice to implement a paper. What does it mean to really use it for real projects? So at the moment, I've only used it to implement specs 2. So I replaced my old action stack with this effect thing, and it's working fine. No specific problem, but I think it's worth really trying it out in a real context. And then we need to add some support to check laws. And as I said, now checking the monadic laws is not so much important, but checking things like the state laws is important. So we need to work on this. That's a young library, still evolving, so there might be some renamings going around and code shuffling, so it might not be so stable yet. And probably there are some missing functions or some missing effects that we might want to add. Benchmarking would be cool as well, because it's supposed to be faster than monad transformers, but it's nice to be able to prove it. And credits, thanks to Oleg Kiselyov, who's the guy who came up with all of this. He's a really great guy, and he was kind enough to answer my questions. And those are some links of the papers that you can read to understand more about monad transformers, and those effects, and how to implement them efficiently. And that's it. That's some extension. So that's it for today. Thank you.